Hello, I'm Jinshin from Dongyun University. From now on, I'll start presenting an assessment of soft textile patch using shape memory alloy. The soft gripper has an end effector made of flexible components for identifying a variety of objects. The characteristics of the soft gripper are soft material, continuous movement, and large strain. In this research, we designed a semi-permanent textile gripper that allows various modes of deformation in complex geometries. From now on, I'll explain the design mechanism of smart morphing textile and research on functional improvements in grip force and deformation degree. The main driving source, shape memory alloy, responds to heat and returns to the state of austenite, the original shape. This new material is lightweight and has the strong restoring force. In smart morphing knit, structure is made of SMA wires and normal fibers through a knitting method. Various figures are available and can be mass-produced with a textile machine. With a knitted pattern, you can bend and twist linear motions to replace them. The bending patterns are as diverse as the patterns of various knits, and the SMA pattern structure that is intensively included in the same area increases the strength. Furthermore, fabrication process is faster and way more simplified than polymer casting. The basic knitting loops are knit and purl. The knitting has a large structural space between the loops, resulting in more strain. Since the power source and the body are all in one, it has a good structure that transmits without loss of power. In this research, a stockinette pattern that contracts in a central direction was adapted. Here, this is a deformation behavior of smart morphing knit that reacts by applying current to a dry patch of 10 well and 10 cores and shows semi-permanent movement over 12,000 to even million cycles. The following is an evaluation of the area, ratio, and performance of the patch. Graph 1 identified the core-swell ratio showing the optimal driving behavior, and the 1-to-1 ratio patch shows the largest strain. On graph 2, it is a bending evaluation for each current magnitude and found that bending occurs well with a large variation of at 0.08 ampere or more. Therefore, although the current value required for each patch area is different, it can be seen that there is an optimal current condition that can efficiently save the energy required for driving. It makes sense to reduce the battery weight of the actuator. By those results, the textile gripper actuator was manufactured by connecting 10 cores and 10 well patches, which are the optimal conditions for smart morphing knits revealed in graph 1 and 2. You can see that the heat is applied with a heating gun to grip a round table tennis ball and a cylindrical shape, and they are quite well gripped. On this page, we focused on strengthening the force and control, so we adopted layer structure. As you can see, textile grippers are very flexible and very responsive to heat, but controlling the exact trajectory and force of the grip motion has been inconsistent. Therefore, a layer structure was applied to control force and strain. This has the advantage of increasing the force by inducing movement in a fixed trajectory by limiting the infinite degrees of freedom. The weight that could hold a coin was evaluated here to withstand the large weight and showed an increase of 1.2 times. The following is the layered placement study and the increased accuracy deflection. In single layer structure here, bending force was too strong that it rolls inside. However, in double layer structure, force was adjusted and made the right path. As a result, layer structure was applied because it is helpful for force and trajectory control. It was placed on the joints of the patch, and the deflection strain developed to a stable angle to hold the object. Finally, we designed a multi-layered textile gripper and performed a motion to grab an object, a motion to lift it up, and left and right. In the future, improvements on critical and stable cohesion work will be continued concerning changes on loops area, and also precise measurement using load cells will be continued. This is the conclusion for the research, and this is the end of the presentation. Thank you for listening.